Let me share screen. All right, so welcome back, everyone. It's good to see you all. Anybody have any particular highlight dish from Thanksgiving, like the best candied yams ever, or an amazing green bean casserole, or no? Stuffing, dressing. Love gravy. Good gravy is good. Good blank is good. Turkey brine, deep fry. Anybody? You brine your turkey? Nobody brines their turkey? Deep frying is good. I think about 10 years ago, I had a deep fried turkey at a friend's house, and it was like, there was this time where like, there were all these stories of the deep fryers getting knocked over and burning down people's houses. so you have to be careful if you're gonna deep fry a turkey. All right, well, very good. So I sent you guys an email last night about the exam stuff. So what I decided is I was gonna give like a midterm this week and then final in a couple weeks, and then I just decided that was too much. And so I'm just gonna give a final next week, right? I sent you guys an email. I'm gonna post a final like next Wednesday, and I think our scheduled date of our final is like a Sunday, so I just put it like do like Friday night or Friday afternoon or whatever, just to make it so you wouldn't. I mean, if you need more time, you can always have a couple more days, but that'll be like 9 days. You'll have the final to do it. But I also adjusted the grading breakdown. It's supposed to be like 20% for each thing, but I just decided, because I'm only giving one midterm, just to make the 40% the higher of the two grades and then 20% the lower. That seemed the most generous, nice thing to do. That's okay. Anybody have a problem with that? You want me to do 40% to be the lower of the two grades? Would you prefer that? No? Okay. And yeah, and then I think I put some stuff down here about, right, just kind of, I added this. And so the final will just be like the second part of what you do with the first midterm, where you just like write up. It's like open, you can talk to people, you just write up nice solutions and turn them in. We won't do that first part. And I'll post it, and then like I'll have a bunch of office hours. I put 11 p.m. Oh, okay, let's say 11. But right. And then any questions about any of that stuff? And then what I decided to do is just have 2 more problem sets until then. So I'll post a problem set soon. You actually already had a problem set about power series. So this problem set will be about Taylor polynomials, the stuff we're gonna do today. So problem set, and then Friday, and then next Tuesday, and that'll be the last problem set. Like a plan. Is plan to get us to Christmas? Okie doke. So what we're gonna do then is we're gonna get into this Taylor stuff, which I previewed a little bit before break. I'll come back to this, but that there is a practice handout, which we'll probably get to maybe like towards the end of class, and maybe carry over into Wednesday. But let me just get back to this. So, in fact, I don't really need the screen, I don't think, for a little while. So get rid of it. Okay. Just the camera. No, the camera's fine. Okay. All right. Let's do math. Math. So we only have 4 classes left, including today. I'm inconsolable. Can you tell? No, I really know. It's fine. It'll be okay. We could keep going. We don't have to stop. I had a freshman in grad school who did that. It's like a graduate seminar. Got to May, thought it was over. He's like, no, we're trying to keep going. Went to like mid-July. You want to do that? You want to keep doing Math 1750 through the break? You can Zoom, right? So it could just, That's okay. Thank you, but no. All right. Well, I'll be doing math by myself. Oh, no, what? Okay. All right, let's talk about Taylor stuff. So this is sort of the whole reason we've been doing infinite series and power series. I give it a good reason. But and I showed you a little bit of that video that I like, which I should link to, but it's not so important. We're gonna go over it all together, but it's just that video has some nice animations and stuff. Taylor polynomials and series is kind of what we're starting. This is the last, this is chapter 10. This is the last chapter we're gonna do in this course. Okay, and so the idea is like, let's just consider a function. So let's consider, here's a function. It's kind of random, but it's a function, square root of 1 plus x. Okay, so if I draw this function, the graph, actually, I guess it's defined at -1, right? So the graph starts here. It looks like the square root graph, but I guess it's shifted over 1 unit to the left. So it's sort of something like that, right? Fair enough. Y equals 1. Okay. So I just want to ask a series of questions about this. And well, yeah, and then we're going to use it to approximate a square root of some number. But let's see. So question. What line best approximates this curve near x equals 0? This is a question you've answered in a previous course. What's it called? The tangent line, right? The answer is the tangent line. So I could draw the best approximation line near x equals 0, and it's tangent line, right? That does not look very tangent. Maybe that, I don't know. Anyways, so the answer is the tangent line. And what do they share in common? Right, we know this from from differential calculus. What do they share? Well, they share at that point, what makes it the best approximation? It's got the same height, so it passes through the same point, and it's got the same slope, right? So at x equals 0, same height, same slope. So in other words, if we call this is f of x, if like, in other words, if let's just say L of x is the tangent line, then I can say the following two things. L of 0 equals f of 0. That's the same, goes to the same point. And L prime of 0 equals f prime of 0. Right? That's just what I'm trying to say. Just that, like, that's kind of another way to say what the tangent line is. It passes through the same point, and it has the same slope, right? Okay, nothing about that is hard, I don't think. But then also, if to find the tangent line, so say L of x is, I'm just going to write it this way, a plus bx. I know we usually do x plus b and stuff like that, but I'm going to write it this way. Okay, then how do we find, so that means, let's see, L of 0 equals a, right? So that's f of 0, which is a square root of 1 plus 0, which is 1. So that's plus 1. That makes sense, same y-intercept. And L prime of x, what's L prime of x? B. L prime of x is B, and that's F prime of x, which is, it's funny, I didn't even put in the 0, but let's just do F prime. What is that? 1/2, 1 plus x to the negative 1/2. Is 1 plus x, we have 1 plus x to the 1/2 power, right? And so actually L prime of 0 equals B equals, actually I guess here we can figure out what B is, right? So that's B, which is 1/2, 1 to the negative 1/2, which is just 1/2. Okay, thus, the tangent line is just 1 plus 1/2 x. Okay, fair enough. That's not something you all already know, but we can find the equation of the tangent line doing this, right? Now, so this is all I feel like. Any questions with this? I mean, this is all should be uncontroversial. This is stuff you did when you first started calculus. I might be presenting it in a slightly different way. But so here's my next question. What parabola / quadratic function best approximates f of x is root 1 plus x near x equals 0. So that's kind of interesting, right? For pretty much for differential calculus, you just did the best linear approximation, but there's no reason we couldn't try to ask about the best quadratic approximation or try to like have a nice parabola that's sort of like, the thing with tangent line is it sort of nicely fits the graph, like when you zoom in and they become more and more like each other, right? And then, but you can almost imagine that this is it's starting to curve downward. You know, it curves sort of downward at x equals 0. So you'd want something that maybe with a little bit of curviness to it. So maybe there's a nice parabola that nestles in there perfectly. You know what I'm saying? Okay, so this is a new question all of a sudden, right? But I think we can probably solve it similarly. We want the parabola, so what, you know, such that at x equals 0, we get the same height, the same slope, and what else? What do we call the curviness part? Concavity, right? Same concavity. Same concavity. Okay, so let's call it Q of x for quadratic to be a plus bx plus cx squared. Okay, and we want to find a, b, and c. You know, find a, b, and c to make this work. To make these work. Does that make sense? Yeah. So if we want the same height, I mean, I'm just kind of trying to follow again what we did on the top board. So, i.e., what do we want? We want Q of 0 to equal f of 0, right? That's the same height. Q prime of 0 to equal f prime of 0. And if it's the same concavity, what do we want? What governs concavity? Second derivative, yes. And Q double prime of 0 to equal f double prime of 0. So this is kind of an interesting thing that we're kind of doing the same thing, but we're just adding another layer to it. And in fact, it's not totally obvious. So let's go through the details that I claim that kind of the A and the B will be the same as we just had up there for the line. Let's check that. So, right, Q of 0 equals A, right? If I just plug in, I'm trying to keep this in mind. This is what our best fit quadratic is. Q of 0 is A, which is F of 0, which we said is 1, right? So A is 1 again. Now Q prime is a little bit different because the derivative is not, the derivative there was just A. I'm sorry, it was just B. The derivative here is not going to be just B anymore, right? So what about Q prime? What's Q prime of X? Somebody say it. Yeah. E plus 2cx, right? And so Q prime of 0 is B again, which is F prime of 0, which we found out there was already 1/2. Okay, we did it up there, right? So just want to make a note, it's the same A and B as before. That's kind of one reason I organized it like this, because each one kind of contains the one before it. Like this is going to contain the best linear approximation too, you know? Okay, now we have to find C though. So C, we need Q double prime, which I think now is just 2C. And F double prime, we didn't compute. But we already know F prime up there, right? F double prime is going to be, what's F double prime going to be? What constant do we get in front? I know you guys can differentiate. Somebody tell me. One third? A half times a half is a third? What's happening? Sorry. We differentiate this, right? What do we get? Yeah, -3. Wait, we drop the power. Wait, we put this in front. -1/4. Drop the power by 1. -3/2. So right. Okay. So -1/4. 1 plus x. Then -3/2. And so Q double prime of 0 is just 2C because that's constant. And we want that to equal F double prime of 0, which when we plug in F double prime, we're just going to get 1 to the -3/2. So that's just 1 times -1/4. So -1/4. And so that actually means C is going to be -1/8, right? Because of that 2 right there. Okay. So let me just write down the result that we found, which is that we found Q of X. We figured out what A, B, and C are, right? So this best fit quadratic is actually 1 plus 1/2 x, like it was before, but now we have a minus 1/8 x squared. Maybe. I should have been circling what A, B, and C are, but so thus Q of X is A was 1, B was 1/2, right? C was -1/8. Okay, so, and does that feel, something about that hopefully feels a little bit good in that it's a downward facing, I guess I just erased the picture of the function, but it's a downward facing parabola. Let me actually plot. Oh, I've left the screen. I just need the screen down now. Let me share. let's just plot both of these just to see what they look like. Actually have this in Mathematica code, but that's fine. This would be just as fast. 1 plus 1/2 x minus 1/8 x squared. Well, okay, so it gets bad quickly, but near, if we zoom in, right, if you zoom in, hopefully it starts to look more like a good approximation there. Oh, wow. That's good, thank you. Maybe we can get something even better. Oh, that looks better, doesn't it? Good call. So it was a tangent line plus some parabola stuff, but that wasn't, and I like not, look how good this is not, because it really follows. Like the blue curve is the square root curve, right? And the red curve is the parabola and the quadratic. And yeah, good. This is much more believable than the previous typo picture, right? Thank you. Does that, it really feels snug, right? It's like really fitting in nicely. I want you to fit in nicely, you know? Okay, so that's the best fit quadratic right there. At least near that point. I mean, obviously it's gonna go away. They'll go away from each other at some point. I mean, this function is not even defined to the left of -1, the square root function. So they definitely can't be the same all the time. But it's kind of neat, right? Okay, so now we can just keep going for an hour and a half and do the best cubic and the best 4th degree and the best 5th degree and the best 6th degree and so on. That's the rest of the semester. We're just gonna see if we can get up to like the 29th degree, maybe the 50th degree. No. So, okay, but let's just think about it a little bit. So first off, there's this interesting question of why the A and the B were the same. And also we can systematize the work a little more, I would say. So, because we're trying to match, you know, F prime and whatever. I mean, we're trying to match the derivatives. So let's just think about best cubic, best, I think a 4th degree polynomial is called a quartic. I don't really know why. Best degree n polynomial approximation. So we can keep asking this question, right? And what we're doing is we're just matching derivatives. So if I have like, let's actually call maybe, let P sub n of x be this sort of, and now I'm going to use constants like this, a1, a0 plus 8 for the constant term a1x, a2x squared, up through an x to the n. So right, so P, so P1 is really just L of x. P2 is Q of x, what I was calling Q of x for quadratic and for linear for line, but I'm just kind of generalizing this. Right, so that's the n degree polynomial. We want the derivatives up to the nth derivative to match. Actually, that's a question I should bring up. For the quadratic, for the parabola, could we have made the 3rd derivatives match? Why did I stop at the 2nd derivative? Up there, why did I stop at the 2nd derivative? Could we make the 3rd derivatives match? Why didn't I just keep going? What's the 3rd derivative of the quadratic? 2nd derivative is that constant 2c, so what's the 3rd derivative? C's of constant. So what's the 3rd derivative? 0. If you take a quadratic and you differentiate it 3 times, it goes away, right? Because it drops by a power each time. So the 3rd derivative is 0, but the 3rd derivative of f is something non-zero. So notice we actually matched all the derivatives we could. we couldn't match the third derivative unless the third derivative that happened to be 0 also. So yeah, so what we do, so like, right, so I guess the idea is that we're gonna match the first n derivatives of P sub n with the first n derivatives of f. Or yeah, I don't know, the first n derivatives, the match up to the nth derivative. We should say match up to the nth derivative is probably a better way to say it. Match up to the nth derivative of P sub n with the nth derivative. It's still awkwardly said, but okay. Hopefully you get what I'm saying. Of f, i.e. we want at 0 to equal the function. We want the first derivative to equal the first derivative, second derivative equals second derivative, and so on, right? Right, that's all I'm saying, right? So we could do the same thing, right? For any size function, we could just keep doing the same. We could play the same game and just like keep doing this for a cubic or a quartic or whatever. Do you believe that? Okay. It's hard to tell after the second derivative what's actually happening. Like the third derivative is the rate of change of the concavity. You're matching those, but somehow that's still matching even better, you know. Yeah. Oh, I didn't stop the share. I'm sorry. Somebody should yell at me. Yeah, sorry guys on the Zoom. I think I just did this stuff on this board right here. Okay, so we're trying to match the derivatives up to there. By the way, I should say something. Even up to the third derivative, sometimes, like you can start having the little tick marks can get annoying. So instead, have you seen this notation? Sometimes they just write like a 3 in parentheses there, so you don't have to keep track of all the tick marks. Sometimes we'll be talking about like the 10th derivative. And so you can even do the same thing here. Like you could say this is like I mean, it's a lot more to write for, I don't know why you would write that, but like you can think of that as first derivative. And sometimes the function itself is considered the 0th derivative, meaning like don't differentiate. So that's like the 0th derivative there, first derivative, etc. Okay, that's just a notational thing because if we start talking about like the 10th derivative, I don't want to have to make 10 tick marks and have you make sure you have 10 tick marks also, right? That would be silly. Okay, so we want to match all these up. Let's actually see how this works in general. So what you can do is you can sort of make a table if you want. Actually, but let me just start listing derivatives of this. So P sub n, actually, let me do this. So this function, this polynomial of x is like this, right? A0 plus A1x plus A2x squared plus A3x cubed up to plus AN x to the n. And so when you plug in 0, you just get that constant term, right? I mean, the point is like, I kind of want to just generalize what we were doing. I don't want to do it over and over again. So I want to try to generalize what we were doing. And then the derivative. Okay, so if we differentiate this, the A0 goes away, right? And we get the A1 plus 2A2x plus 3A3x cubed up to plus n AN x to the n minus 1. We differentiate that. The n comes down in front. Did I mess it up? Yes. That should be x squared, right? Thank you. Yeah, so I'm just differentiating. The coefficients are just constants. So what if we, so that means the first derivative, I might even stop writing the sub n just to like, I feel like the p sub n gets in the way of what we're trying to do here. It's a polynomial, right? So let's say, yeah, let's just do it this way. So p prime of 0 is just a1 now, because if you plug in x to all these, they go away. Or you plug in 0 for all these, they go away, right? So keep going. I feel like it's boring to watch me. So keep going for a few minutes and see if you can write down a few more, like what the second derivative is, the third derivative. Do that with your neighbors. Just keep this going and see like what you should be able to write down p double prime of x. And so hopefully people can see this. And check with your neighbors, and I'll stand here and drink coffee. The cool thing would be if you can get the pattern. There's a pattern. The best Apple Pencil is your finger. Check in with your neighbors. See if they're getting something similar. You might have to think about the fourth term here. There's like an a4x to the fourth that I didn't write. I'll write that in. Get back to where you want to go. Get back. Get back. Well, the clock's fixed finally. Okay, that's good. The clock was stuck for last week or so. You guys get the second derivative. Is that what you guys got for the second? Maybe. So what happens when you plug in 0? What do you get? 2a2. It's nice to notice, I mean, you might want to notice something like, it's kind of nice that we're just getting one constant. It's not some combination. If you think about it, when we differentiate twice, everything below the x squared disappears because we differentiated it away. When we plug in 0, everything above the x squared, above that term disappears. So that's kind of like why we're just getting that term, which is a nice thing to think about. So this is just 2a2. You guys, what about the third one? What's it going to be? When you plug in 0, what do you get? Yeah. 6a3, because if I differentiate again right now, this will go away. This will become constant because that was linear. 6a3, this becomes 24a4x. And then we could keep track of this, n times n minus 1 times n minus 2, a sub n, x to the n minus 3. It's kind of annoying to keep track of, but we could do it. But it's just nice, again, if we plug in 0, all the terms with a0s, a1s, a2s differentiated away. All the terms with a4s and above, we plug in x equals 0, go away. And so we just get p triple prime of 0 to be, I should use the 3. Third derivative is 6a3. And you can kind of identify what the fourth derivative is going to be. What's the fourth derivative going to be? 24a4. Is that a pattern? Yes. Emily strongly says yes. What's the pattern? We get a sub n, and then what's this constant here? This is 4 factorial right here. In fact, we got it by multiplying 4 times 3 times 2, right? Get this term, we differentiate once, got a 4, differentiate again, 4 times 3, differentiate again, 4 times 3 times 2. And so you really are getting, yeah, so it's worth noting, this is actually, this is 4 factorial times a4. This is 3 factorial times a3. This is 2 factorial times a2. This is 1 factorial times a1. And this is actually 0 factorial times a0. Have we talked about 0 factorial being 1? Have we talked about that? We did. I got one nod. 0 factorial is defined to be 1. Is that weird? It's not weird. Why? Why is it? Why do you like it? So like from 5 factorial to 4 factorial, you divide by 5. You divide by 1. Interesting. That's a nice way to look at it. Like you can sort of go from 1 factorial to the next just by multiplying a number or dividing the number. Yeah, I like that. That's a good argument. 3 factorial is 6. 4 factorial is 24. So to go this way, we multiply by 4. But to go this way, we divide by 4. And you're saying if you keep going up, right? So we divide by 3, divide by 2, divide by 1. So 0 factorial is 1. Sorry, I don't know if you can see that. But yeah, interesting. I like that. That fits the pattern. There's also this sense that what 0 factorial should be multiplying nothing together. And it seems weird, but if you add nothing together, what should that be? Nothing, 0. But why? It's because if I start with something and add nothing to it, then I have to add 0 to add nothing to keep it the same, right? But if I want to start with something and multiply by nothing, not multiply by anything. I'm not saying multiply by 0, I'm saying not multiply by anything. I take like the number 7 and I want to multiply by not multiply by anything and keep 7. What am I really multiplying by? What number am I multiplying by? 7 times 1 is 7. So a multiplicative empty thing should be 1 and an additive empty thing should be 0. That's another way to think about it. It's kind of strange, but it's like because of the additive and multiplicative identities. Anyways, but Ahmed's explanation is actually kind of nicer to fit the pattern. Okay, so that 0 factorial is actually 1. So this actually fits the pattern. So in general, you can actually see this. In general, I should write this in bright colors. in general, the nth derivative of a polynomial at 0 is actually n factorial times a sub n. That's the point here. This is the pattern. Okay. And because of that, I'm saying we're trying to match derivative. Okay, so like, yeah, this was a whole separate thing. It's like we completely forgot about our original function f. And we just went over here for a while and we're like, let's mess with this for a while and see if we can figure out the pattern. But you remember the whole point is we wanted a polynomial whose derivatives match the derivatives of the function, right, that we were looking at. And so if we want to match, derivatives, then I'm not on the share screen or anything. If we want to match derivatives, it's kind of neat though. You differentiate n times and you get an n factorial. It's really just doing the power rule over and over again. X to the fourth becomes 4x cubed, becomes 4 times 3x squared, becomes 4 times 3 times 2x. Right? You're just doing the power rule over and over again, and it's creating this factorial. Yeah, so okay, so to match, let's see. So really what we want to do, so if we want to match derivatives of this polynomial with the derivatives of f, let me just write that again, just to remind ourselves what we're doing. We want to match really as many derivatives as we can. And that was the idea that once you get past the, if you have a polynomial degree 5 and you differentiate it 6 times, it goes away. It becomes 0, right? So we can only match up to the 5th derivative because you can only control up to the 5th derivative. So we want to match as many derivatives as we can between our original function f of x and our polynomial p of x. Okay, and so if you think about it, if we're trying to set the nth derivative p sub n of 0 equal to f sub n, not sub n, the nth derivative, sorry, the nth derivative of p equal to the nth derivative of 0, nth derivative of p equal to the nth derivative of f, the nth derivative of p equal to the nth derivative of f at 0. I've been trying to say it 7 times. But we have a formula for this. This we can replace now with n factorial times a sub n. And a sub n are the coefficients are what we're looking for. I mean, I guess I'm using the letter n. Maybe I should have used the letter k or something. Actually, yeah, I'm kind of wishing I'd used a k up there or something like that. But because I want n to just like be all of them. Like I want n to be the arbitrary one. Let's just say this is, let's call this k. Sorry, I meant to do this actually. It doesn't really matter because I dropped it at some point. But in general, right, the nth, it still doesn't change what I just said. Okay, so this equals the, and what we're looking for are those coefficients, right? That's what we're looking for, are these coefficients. That's what we did with the quadratic and the linear. Look for these coefficients. And then now we have a formula for the coefficient. It's actually a sub n is the nth derivative at 0 over n factorial. Okay. And that's actually the big formula. That's actually the big thing that controls all of this. And it seems really abstract, but let's check it against what we just did. Like here's this q, this second degree function, right? So let's just check it against our example and then let's continue. Let's check with f of x equals root 1 plus x. Right? So here's where I say what you can do is you can organize this in a table. You can say n here, here's 0, here's the nth derivative of x, Here's the nth derivative when we plug in 0. And here's the nth derivative when we plug in 0 divided by n factorial. Because this is what we want to compute, right? If I'm saying there's this nice formula. So here we have the function 1 plus x to the 1/2. What I'm going to claim is that the first few numbers we get here will match the quadratic that we just had. And then we can just continue. So we plug in 0, we get 1. We divide by 0 factorial, we get 1. So the first derivative, actually, it's nice to just sort of fill these in column by column. And let's just differentiate over and over a bunch. Right, that's what we found for the second derivative just by using the power rule. So what's the third derivative? What power rule says the coefficient in front is going to be what? Yeah. Yeah. So in fact, start filling this table in. Maybe again, like, let me just let you guys do it, because otherwise you're just copying me and it's not very interesting for you. But I would fill in maybe up to like, yeah, up to like the sixth derivative. It gets kind of, might start to get sort of unpleasant. You can stop at the fifth if it gets too unpleasant. And then you can start plugging in 0. And then you can start dividing by n factorial. I claim you'll get the coefficients that we had. Then when we get some more coefficients, we can plot and see if we get a nicer, like a thing that even fits the square root graph even more nicely. I'll do the easy thing, which is I'll plug in x equals 0. Check with your neighbors again, see if you're getting the same thing. Sadly, there's not really like a super nice pattern of the derivatives. You're sort of multiplying by odd numbers on top and powers of 2 on the bottom or something, but it's not. It should be alternating plus and minus probably. Are we having fun? Are we doing it? Having fun? Yes, no. Okay, so this one is minus 15 over 16, right? Subtract 1 again, you get minus 7/2. That's what you get. Next one, can you tell me what the next one is? Yeah, 15 times 7 is 105. 32. 1 plus x to the negative 9/2. We can do one more, right? negative 945 over 64. Yeah, this gets kind of tedious at some point, but it's, you know. Okay, so we plug in 0. I mean, yeah, we plug in 0 and these all just become, powers just become 1. Oh man, now we have to divide by n factorial. Because this is the column we really want. This is the column that gives us the coefficients of that polynomial that best approximates, right? So here we had 1/2 over 1 factorial is still just 1/2. Here we have to divide by 2 factorial. What's negative 1/4 divided by 2 factorial? Negative 1/8. And that's what we got, right? When we did the quadratic, we got negative 1/8. And we actually did divide by 2 if you look back. We actually divided by 2 at one point. So now 3/8 divided by 3 factorial divided by 6. 3 over 48, which I think is 1 over 16. Oh, now it gets bad. Negative 15 over 16 divided by 4 factorial, which is 24. I mean, maybe a little bit. There's a 3 on the top and bottom that cancels. Actually did it in my notes. Do I have it? I think that's what I have. Yeah, okay. So I think a 3 on top cancels, and I think this is negative 5 over 128. And then it begs a question of, should we keep doing this? This 105 came from 3 times 5 times 7, 32 over 5 factorial. 1 times 2 times 3 times 4 times 5. 3 and the 5 cancel, 7 on top. 256 on the bottom, 7 over 256. Fun. All right, I'm not going to do the next one. You don't really have to. Tempted to do the next one, but I really should not probably. Okay, so I want to put the right. I'm going to write etc. right there. Okay. So. All right, so the point is, we can actually write down, for example, the best fifth degree approximation. So that's what we've done up the table up to 5, really. I mean, we could do 6 if we wanted. But the best fifth degree, the best quintic, it's called a quintic. It's not a word you need to know, but it's the best fifth degree 5 approximation. So, for example, the best fifth degree approximation of square root of 1 plus x near x equals 0 is, we just put those as the coefficients. 1 plus 1/2 x minus 1/8 x squared plus 1/16 x cubed minus 5 over 128 x to the 4th plus 7 over 256 x to the 5th. Right, so that's what you're doing. That's what you're just using the last column of that table. Just that was really just to organize the work, really the table up there. Let me try. I'll share screen in a second, but let me make this longer. 5 over 128 x. Oh, I forgot the 1/16 plus 1 over 16 x cubed minus. But am I getting you to not lose the forest for the trees here? Like what we're actually doing is trying to find this best fit and make all these derivatives match, and that's kind of what led us down this path. Hopefully I typed that correctly. Did I not? Ooh, that's kind of fancy, right? Again, it's not good after a certain point, but it really is indistinguishable from, it's hard to see, like they start to deviate from each other here. And if I keep zooming in. No! How did I do that? Okay. Somehow it's funny. Oh, that's even better. Look. It's yeah, it's weird how you can't see. I mean, I feel like I should be able to see if I did something. Like, what if I made this like, minus 50? I want to see something that looks bad. Hey, that looks bad, right? So it's good. If you change that, you can definitely make it look bad. It's not like but it still looks pretty good near 1. It just, because it's working for the quadratic, it's working up to the, the slope, the height, the slope, and the concavity are all working. It's just you lose something at some point. So, okay, what was that? 1/16 plus 1/16. Oh, geez, I forgot to share screen. I'm an a-hole. Let me do that. Sorry. Let me share screen. I've just been looking at. Okay, I was mistyping it anyways. Okay, so if I typed out this whole polynomial correctly, then we get this 5th degree polynomial that does near, yeah, actually, this is peeling off farther away than it was before, I think, when we had the wrong, when I had that x cubed twice. So you get this amazing approximation. And by the way, like if you want to do you can approximate certain things. Like what if I wanted to approximate the square root of 1.5? Right? Just as an application. By the way, this is called the Taylor polynomial. I should say this has a name. This is called the Taylor polynomial. Of degree 5 for f of x near x equals 0. Okay, that's what's called. It's called Taylor polynomial. It's the best. It's really just the best fit near that point. Application. You can approximate. I mean, again, I sort of mentioned that this is actually how calculators work. The calculator doesn't know what the square root of 1.5 is, but it could plug in, like, if I use x, well, let's just say, so let's approximate square root of 1.5. So we can use x equals 0.5 in the Taylor polynomial, because that's right. Like if I put in 0.5 up here, then I get the square root of 1.5. Does that make sense? Okay, and then if we do that, so because these are very good approximations, then we should get to the square root of 1.5 is approximately 1 plus 1/2 times, I guess I just want to use a half, I just say a half. So 1/2 times a half minus 1/8 times a half squared plus a 16th times a half cubed. I mean, think about before computers existed. Not that this would have been fun to do by hand, but how on earth would you ever know? And we'll do this for worse functions too, right? How would you ever know what some value of some function was? You really need to use these techniques. So this will be fun for me to try to type in. Make this bigger so you guys can see if I mess up. So 1 plus 1/4 minus an eighth times a fourth is a 32nd plus 16 times 8. 16 times 8 is 128. I just know powers of 2. Plus 1 over 128. Minus 5 over 128 times 16. I'm not going to try to do that. I think it's, I know what it is, but plus 7 over 256 times 32 on the bottom. 56 times 32. Wait, the parentheses there, I think. Okay, did I type that correctly? Maybe. Oh, okay, yeah. Okay. Square root of 1.5. Not bad. Yeah. 3-digit accuracy. No, what are you laughing at, Evan? Seems ridiculous. I typed it in. It's dedication, man. Yeah, so that's nice, right? So this is actually a lot of times how computers actually do stuff. They would just use more terms to get better approximations. And there's definitely fancier techniques than this, but this is at least one of the first ways you could see how to do it, okay? So we get about, which one was the actual? 1224976. 0.224976. And the actual value here was 1.2247 something. 4745. So that's not too bad. Okay. So let me just say like what we did here, the general thing. The general thing is we have this formula for the nth Taylor polynomial at 0. And sorry, I know we haven't had a break, but now we're actually like, I think I'll just let you guys go a few minutes early instead of having a break. Is that fine? Okay. That took a while. But all we were doing was trying to make derivatives match. And this is kind of where you're inevitably led. So in general, the nth degree Taylor polynomial for f of x near x equals 0 is, well, it's a statement that's going to look weird because these are all constants. Let me just start writing it. So it's this kind of thing where basically we're putting the nth derivative at 0 divided by n factorial in front of each x to the n, right? Plus dot 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 plus, I could do the n minus first, minus 1 factorial, x to the n minus 1, plus the last term, which is the nth derivative. The nth derivative at 0 over n factorial, x to the n. That's kind of what we just did there. We took the last column and put them in front of the corresponding powers, right? That's really all I'm saying here. And we could write that as in summation notation, right? It's really, this should be the kth, yeah. Why do I keep doing this? I like n to be my index, not to be my power. I'm sorry. Let me write the kth one. So just turn all these in so far into k's. It's like if I want the 10th degree polynomial, I have to do the 0 through 10th derivative, right? So this is n equals 0 to k, because also we're going to let k go to infinity to get this thing called the Taylor series. We're going to just let it, where it's going to get this infinite polynomial, basically. And what we have, it's what I wrote up there, is that formula is the coefficient of x to the n. So it's the nth derivative at 0 over n factorial times x to the n. So this is kind of the formula. I always like to write summations out in terms also, but does that make sense? I mean, hopefully with the example, this looks very intimidating, but really these numbers are just what we computed in that table right there. And we did like k equals 5 because we got bored at the 6th. We didn't want to actually compute the 6th. In the last column? Yeah, that's the thing. Okay, so that's the thing that's cool that notice when we did the linear to the quadratic, the linear piece was the same. And you just added the quadratic term. And because of the way the polynomial differentiation works, we got that the coefficient only depended on, or the nth derivative only depended on the nth coefficient. So it does subsume all the ones before it, which is nice. Like if you want to go from the quadratic to the cubic, you just have to find the cubic term. So if you've already computed the Taylor polynomial degree 5, to get the Taylor polynomial degree 6, you don't have to start all over again. You can just add another line to the table, right? So cool. And then the idea will be that we will actually, like this is a finite polynomial. This is kind of ugly. We're going to see some ones that have nice patterns. I want to start with one that's kind of just like ugly and random, just shaking to do this for any function. One of the big things we'll do for the next week and a half is like, we'll actually look at, like, we already saw cosine has like a nice pattern to it. And e to the x is going to turn out to have a nice pattern. And stuff like that. So a couple things, actually, maybe we'll do e to the x because that one's really simple. And that's kind of nice to do. And it also gives a nice way to approximate e. And that's something we could fit in 10 minutes. Okay, let's do that. One thing I will say that I'll have to do next time is, what if we don't want to do near x equals 0? What if we want to do like near x equals 5? It's a little annoying, but we really just turn this to a 5 and change this to an x minus 5. Remember we had power series centered at different points. So like when we had x minus 5 to the n. So it's going to turn out not to be that bad, but I'll have to talk about that with an example. But let's just do e to the x because it's a fun one and there's a nice pattern. And you can sort of see what's going on. And it was actually on the homework due Friday before break. There was that problem where it's like, like the last problem was like, try to identify this function sort of thing. So let's actually see this. So let's do one more example. And then we'll just call it a day. So example, f of x is e to the x. Nice function. So let's make this table. Because we know we want to compute, I mean, if we're thinking about this formula here, we know we're going to need to compute the nth derivative at 0, right? And so let's just compute the nth derivative in general. Let's compute the nth derivative at 0, and then let's divide by n factorial to get the coefficient. Okay, the function is e to the x. What's the derivative of e to the x? Oh, e to the x. So the first derivative is e to the x. What's the second derivative? E to the x. E to the x. We just keep differentiating. That's nice. That was nicer than that one by a fair amount. Yeah. You're like, why didn't I start with this example? No, it's well, because this ends up being the nicest example. Hey, that's nice. So what happens when we plug in 0? 1, 1, 1, 1. Whoa, my things were getting off from each other, but okay. Doesn't matter. And then we divide by n factorial, 1, 1, 1/2, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial, 1 over 6 factorial, etc. Right? So the Taylor polynomial for e to the x of degree 6, say, we can write it down nicely, right? It's just, we just use those as the coefficients. So Taylor polynomial of the 6th degree, let's just say 6th degree, but you can see how to generalize this easily. For e to the x near x equals 0 is 1, I'm just using these as the coefficients, right? 1 plus 1x plus 1/2 x squared plus 1 over 3 factorial, which is 1/6 x cubed plus 1 over 24 x to the 4th plus 1 over 25. No, that's not what 5 factorial is. 120 x to the 5th. And 6 factorial is 720. No. Yes, 120 times 6 is 720. 1 over 720 x to the 6th. Okay. And if we plot, we can plot, right? Plot e to the x and 1 plus x plus 1/2 x squared. Please catch me on typos. Oh, 1/2 x, 1 over 24 to the 4th. Should I just stop at x to the 5th? Let's stop there. Let me share screen. Yeah, okay, well, this is not obviously good. Let me zoom in vertically. Well, that starts to look good, right? Yeah, see how it's following the graph so nicely before it peels off? And then here, you know, the e to the x goes towards the x-axis. You go that way. So eventually this has to peel off also and go away because it's a 5th degree polynomial. But is that kind of nice? Such a good approximation. And that also means approximate, we can use this to approximate E. By the way, if I wanted the, you know, the 10th degree Taylor polynomial, I could just do the same. I mean, you could just see the pattern. It's going to be 1 over 7 factorial x to the 7th and so on, right? So we can use it to approximate E. E to the 1, you know, E is e to the 1st, which should be about what we get when we plug in 1 here. 1 plus 1 plus 1/2 times 1 squared plus 1/6 times 1 cubed plus 1/24. In fact, there's this crazy thing that it's like you're summing 1 over factorials, right? We get 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1 over 120 plus 1 over 720. And if you wanted to keep going, you could, right? And get better and better approximations to E. So, oh, I forgot to stop the share, didn't I? Stop the share for a second. I just wrote this about approximating E by plugging in x equals 1 to the polynomial we had there. And if we do that, okay, so one more time. Let's do, so that we get 1 plus 1 plus a half. I'll just call that 2.5 plus basically 1 over factorial, right? So 1 over 6 plus 1 over 24. You can actually see it doing. So you get that if I add up the first few, like 1 plus 1 plus a half plus then 1 over, yeah. Versus E, you know E? Will it give it to me? No. Where's the calculator? 2 plus 3. E. 2.71828, 1828, 2.7180. So again, we've got a good number of digits. So like, yeah, how do you figure out what E is? E is this kind of weird number that comes up in like continuously compounded interest rates, or like the function is derivatives itself. But how do you actually calculate that number? This is actually a really nice way, a really fast way, because these numbers, as you add more terms, get small really quickly. Because factorials grow really fast. And so you can actually get a lot of digits of accuracy just by doing this. So this is, yeah, what did it say? Nope, that was actually E. Yeah, I remember E has this 1828, 1828 repeating in it, which is kind of weird. 1828. This was, so here we got 2.71855 versus the actual value 2.71828. I guess. Yeah. Cool. Now you know what E is. Tell your friends. Be like, dude, I know how to compute E. How many digits you want? Let's do it. You gonna do that at lunch today? No? I'm very sad. Okay, let's call it early. Sorry I didn't get the break, but let's just call it a day and then we'll continue. We'll talk about scenarioing at different points. And then I have a handout to let you practice some of this yourself. And yeah, we'll continue from there. All right, guys, take care. And I'll post the homework, which will be on this stuff also for Friday. All right, bye-bye.